Okay. Now, this is the last week of new material for test 2. As I mentioned last class, the practice test and its solution are already up on the home page in Canvas. I just realized I don't think I'd put them up on my own site yet. No, I still need to do that. So when I post the notes for today, I will put the practice test there too. Okay. Just want to get those transferred. Okay. All right. So we have these two lessons, lesson 27 and 28 for this week. Next Monday will be review. There will not be class on Wednesday, April 7th. So the test will be posted around that time, if not before. So then to give you a little more time to focus on that. And after that, there won't be much. There'll only be 3 lessons after this week's material, and the final will be comprehensive, a mix of old and new problems. So what you've been practicing for tests 1 and 2 will be helpful for the final also. Okay, so let's see, one last attendance check. Okay, so let's get into lesson 27. So method characteristics is an approach for solving certain PDEs that are first order in time and space. So the problem we're going to look at is one of this form. Now this problem is linear because the coefficients a and b depend on x and t, but they do not depend on u. If they did, that would make it a quasi-linear PDE, but we will talk about that case a little later on. So here's our PDE, and we're not dealing with boundary conditions. This is defined in the whole real line. Looks like a Cauchy problem, and then we have this initial condition here. And the way we're going to come up with a solution is to make a change of variable. All right. So let's see. So by changing variables x and t to new variables, if we select the new variables tau and s in terms of x and t properly, we can make this PDE, basically reduce it to an ODE in a sense. Okay, so to find out what is the right change of variable, we're actually going to define these initial value problems. So here we have ODEs. So dx, ds, and dt, ds come from the coefficients of a PDE. So the coefficient of du dx belongs in the ODE for x. The coefficient of du dt belongs in the ODE for t. So x and t, of our independent variables, they're also the solutions of these ODEs. And we also have to specify initial conditions for these ODEs. If you look at where our initial condition is defined, it's on the x-axis. So in other words, t equals 0. So t equals 0 is the initial condition for our ODE for t. And then at time 0, x will be equal to tau, so it's our other new independent variable. So you can think of tau and s equals tau and 0 as being a parameterization of the initial curve, which in this case is the x-axis. So by initial curve, I mean where the initial condition is specified. Now, and generally in our examples, the initial condition is always specified on the x-axis. Although there are problems for which that's not the case. Okay, so the initial x value goes here. The initial t value, which in all of our examples has been 0, goes here. So x and t are now thought of as functions of the new independent variable s, and the additional independent variable tau you can think of as a parameter. Now, the reason why we solve these ODEs is from the chain rule. We go back to our PDE. Well, A is dx ds, and then B is dt ds. So if I fill that in here, I have ux xs plus utts. By the multivariable chain rule, this whole expression here is du ds. So now the PDE is reduced to this, du ds plus cu is equal to 0. Well, this is an ODE for u in terms of the single variable s. So now we can go ahead and solve this to get our solution u. And the initial condition for this ODE comes from the initial condition for our original PDE. It's f of tau, because tau is equal to x on the x-axis, t equals 0. All right. So it's these three ODEs that we will now use to solve the original problem with these three accompanying initial conditions. So the way it always works for these problems, coefficient of ux goes here, coefficient of ut goes here. For a typical initial condition, tau is the initial value for x, 0 is the initial value for t. And then for your simplified PDE that's now an ODE, whatever other term we have here is included here. So it's this part of a PDE that gets condensed to du ds. So what we could do is then work on solving these ODEs. And we actually get an expression for the solution u, but it's in terms of the new variables tau and s. Ultimately, we need to express u in terms of the original variables x and t, and the solutions of these problems will help us do that. Okay. Now, this whole approach to solving PDEs of this form is called the method of characteristics. And the variables tau and s, those define what are called characteristic curves. So characteristic curves are defined, these are curves in the xt plane that depend on a parameter s. And they all start from these initial points on the x-axis. So basically, the initial data propagates along these curves. So the meaning of these new variables, tau and s, is the s coordinate indicates a point along a curve. So each characteristic curve is parameterized by s. The tau coordinate indicates the initial point for each curve. So each curve corresponds to a particular value of tau, because that's where it begins along the x-axis. And then as each curve, as time moves forward, these curves are defined in terms of a parameter s. Okay. So what happens is whatever value of initial data has for a particular characteristic curve located at the point tau, that initial value is basically carried along that curve. That starts here and progresses according to the solutions of these ODEs here that define how the curve traverses through XT space. So now I'll show some examples of how the method of characteristics is used. So here's our example problem. Let's see, we'll start this on a new page. Okay, and with our initial data. So then we write down the ODEs for our characteristic equations. dx/ds is a coefficient of ux, which is 1. dt/ds is a coefficient of ut, which is also 1. So now we can go ahead and solve these by integration. So if you integrate both sides with respect to s, because it's dx/ds, then what we will get is x. You integrate this with respect to s, you get s with a constant of integration. And the constant of integration is determined by the initial condition. So it's, in this case, it would be tau. So you take a derivative of this with respect to s, and you get 1. You plug in s equals 0, and you get tau. So this is a solution to this initial value problem. And then similar for here, except your initial value is 0. So t just ends up being equal to s. Now, when it's a linear PDE like this one, it's always possible to solve these independently of the other ODE for u, because the coefficients of ux and ut will never depend on u when it's a linear PDE. When it's quasi-linear, there is a dependence. And we'll see that in the next example. Oh, wait. Oh, no, actually, that's something I'll cover on Wednesday. So what happens to our PDE? We get du ds plus the rest of a PDE plus 2u is equal to 0. So remember, this part, whatever we have here, it always becomes du ds. And then this is the initial value. Now, how we can solve this is it's a separable equation. It's also a linear equation. So you can use either approaches for solving either kind of problem for this one. The solution turns out to be e to the minus 2s sine tau. Okay. Now to show you where that comes from, in case your ODEs are rusty, I can rearrange this to get du is equal to, so I can move this to u to the other side. I get minus 2u ds, and then I want to separate the variables. I want to have left side depend on u, right side depend on s. So I'm going to divide both sides by u. So then you can integrate both sides. So I get natural log of u is equal to minus 2s plus a constant of integration. We get u is equal to e to the minus 2s plus c. Now, to figure out what the constant of integration must be, I could also write it this way, e to the minus 2s, e to the c. But I can call that c tilde, because this is an arbitrary constant, therefore this is also an arbitrary constant. To find out what the arbitrary constant must be, you can set s equal to 0, and you just get c tilde, so that must be equal to sine tau. So that's where this solution comes from. So now we have a solution, except it's in the wrong variables. It's in terms of s and tau. So what we need to do is go back, go to these to express s and tau in terms of x and t. So when we do, well, we found that t and s are the same. So I can just replace s with t here. And then as for tau, if I go back up here, I can solve this for tau. Tau turns out to be x minus s, but s is t, so tau turns out to be x minus t. And that's what goes in here. So from your PDE, write down the ODEs for characteristic equations with initial conditions. And we also have a reduced ODE for u. So really, you could write down all three of these at the same time. And then you go ahead and solve them to express x, t, and u in terms of the new variables, s and tau. And then you use these solutions to express tau and s in this solution in terms of the original variables, x and t, so that you can get u of xt. So questions about what happened here? Okay. Now I'll do another. Okay, so now we have a variable coefficient. So we have x as our coefficient of du dx. And then the coefficient of ut is still just 1. And then we have this variable coefficient of u here. And we have some general initial conditions. So it's capital F of x for whatever that might be. So what we get for characteristic equations for x and t. Oh, typo. All right. So coefficient of ux goes here. Coefficient of ut goes here. The initial values would be tau for x and then 0 for t. So then we can go ahead and solve these. Now, what we get for the solutions, well, t just turns out to be s again. This problem for t turned out to be exactly the same as in the previous example. Here, be careful about this one. A common mistake that I see students make is think, okay, this is an ODE depending on s, so you integrate both sides with respect to s, and you get you might get something like xs, but that's not true because x is a function of s. It's also your unknown. All right, so just keep in mind, what we're saying is x is equal to its own derivative. Well, what function is equal to its own derivative? The exponential. So that's why x is e to the s, and times a constant. So anytime a function is its own derivative, it's a constant times e to that variable, the independent variable. Now you could also solve this by treating it as I did ODE in the previous example. It's a separable equation, so you could solve it that way. But this is one of those good to know things that if you have a function equal to its own derivative, it's the exponential, or if there's a constant here, then that constant goes in the exponent. So here we have a solution to that one. And then the PDE gets reduced to this. Now, we want to express this coefficient in terms of characteristic coordinates. So that's why we don't have t down here, we have s. So t has to be expressed in terms of s and or tau, and that's what goes here. Now, a solution to that is this, and I want to show you why. What you have is, if I can rearrange this to get u on one side and s on the other side, I get 1 over u du is equal to minus s ds. And then when you integrate, you get natural log of u is equal to minus s squared over 2 plus a constant of integration. So then you exponentiate both sides, you get u is equal to e to the minus s squared over 2 times an arbitrary constant, which would be the initial value, f of tau. That's what goes here. Okay. So now we have our solution, but we still need to express s and tau in terms of x and t. Now s is t, so that part's easy. But then for tau, we need to solve this equation for tau. Well, tau is x e to the minus s, but s is t. So we can fill that in. And this is our solution in terms of the original variables. For whatever given initial function capital F you have. All right, so are there any questions about what happened in either of these examples? Or about any homework problems?
Less than 24, 3.
24?
3.
But I will confirm less than 24?
Number 3.
Yeah, yes. I'm trying to confirm the lesson number. It is less than 24, correct?
Yes.
Yes, that's what I needed to hear. Thank you. Okay. All right, here we are. Okay, let me. Okay. Your question?
I'm not sure how to visualize the solution of PDEs.
Okay. All right. So what happens when you have a so the key thing here that when I talked about this in class was for the 3D how it's to be interpreted. Um, in terms of does a solution have a sharp leading edge or trailing edge? Because what's happening is you have this initial data that is 0 almost everywhere, and so to give you an idea as to what's happening, imagine how a solution behaves at a point that is far away from where the sphere is, of radius 1. So this, because based on Kirchhoff's formula for the 3D wave equation, okay. So this is what we have here in the 3D case. It's going to be equal to t times the average value of this part of initial data over a sphere that's centered at a point XYZ, and a radius is CT, where C comes from here. So if you're examining a solution at a point that is far away from the from the origin, so well outside this sphere where the initial data is equal to 1, you're taking the average value of this initial data over a sphere centered at XYZ and radius small when t is small. So if you're just a little ways past t equals 0. Well, the average value of initial data over a sphere that small and not overlapping this would have to be 0, because there's no non-zero initial data there. So that's how the process would, the solution of a behavior would start. So what this problem is asking about is what happens as t advances. And really I'm more interested in what happens in terms of words. And if you like, you can try to use pictures to illustrate what you're talking about. So really, and the thing is, since we're in three-dimensional space and your solution is a function of x, y, and z, so we're really talking like 4 dimensions altogether. Even if you're focused on what's happening at a specific time, you still have x, y, z, and u to consider. But if you like, you can kind of flatten things to 2 dimensions just to for a purpose of illustration, because when the solution is 0 or not has a lot to do with, if you're like what we could do is illustrate what's happening at a sample point, x, y, z, somewhere in space, and you can just focus on what's happening at that one point. And the solution at that point will depend on the interaction of this initial data with a sphere, and just the boundary sphere, not the ball inside, but just a sphere that's centered at your point x, y, z, where you're examining a solution, and radius ct. If you want, you can assume that c equals 1. So the discussion I gave about how a solution behaves in 3 dimensions is what comes up here. So the behavior would be based on that.
Okay, thank you.
I had a question on lesson 20, number 7.
Okay.
Yeah,
Okay.
So do you want like us to describe in words how to solve, or to actually solve and like have an equation?
Okay. 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 I'm not looking for you to get all the way to a solution formula, but I would like to know how you would proceed. In particular, because the PDE is non-homogeneous, how is that going to be taken into account? I want to know, how does that affect your solution process? And what I would recommend for that is keep in mind, when non-homogeneous PDEs have come up elsewhere, how does that affect things? So it's the same idea.
So similar to like with the heat equation, I remember doing something like this one time, where we had to kind of show how to make it homogeneous. Is it similar, or?
No.
Oh, okay.
Hold on. That's boundary conditions.
Oh, okay.
You transform a problem, and actually, when that happens, your PDE becomes homogeneous. No, because okay, think of it this way. This lesson's about finite Fourier transform, and the point of a finite Fourier transform is to reduce the PDE to an ODE, where the ODE depends on a parameter. In this case, the parameter being oh wait, I'm sorry. Okay, I apologize. I got my lessons mixed up, but okay. Because yeah, I guess finite Fourier transform comes up in a future lesson. Okay. Now, because this so what this lesson actually does cover for wave equation on a bounded interval is how you can use separation of variables. But separation of variables, as it's described, is only useful for homogeneous PDEs, also homogeneous boundary conditions. It cannot be applied directly to a PDE such as this. However, that was when we saw separation of variables for the heat equation. We were able to use certain things from separation of variables in lesson 9 to handle non-homogeneous PDEs, and that led to the method of eigenfunction expansion. Because what happened in that case is, and this part, at least it's part of my lesson mixed up, does still stand. You reduce the PDE to a family of ODEs, and from expansions of all the particulars of a problem, like your initial data, your source term. So what would happen in this case? So you want to use that same kind of principle to solve this. And what I want to know in particular is what kind of ODEs would you get, and how would you solve those ODEs? What happened in lesson 9 kind of gives you a template.
Thank you.
Mm-hmm.
I also have a question. It's the same lesson, number 3. So, I guess I have multiple questions about it. I've kind of gone about the unbounded case, and I think I've got that fine. But the way I'm reading the question, should I read it as, I mean, is it okay if it's, for instance, just unbounded, or should we find an unbounded case and a zero case?
Okay. Yeah, actually, let me return to what they're talking about here. Okay, this situation. Okay. And actually, the boundary conditions for this problem. Okay. Yeah, you should be able to find a case where you get a solution that must be 0.
So I guess working with the, okay, greater than, okay.
Yeah, so you have a couple different scenarios to consider. So one produces unbounded, one produces 0.
Right. Okay. Thank you.
Yep. Okay. Any other? Okay, well, wow, short class today, even with questions. Okay, but yeah, I guess the material I had for this lesson turned out to not be very lengthy, and I think the same is true, or will be true on Wednesday. So that would also be a good time to bring any homework questions that you might have. I do have a small backlog. Okay, so here's what remains to be graded. I see some homework 6s, homework 7s. Okay, not too many though. So I will be sure to have all of that graded, and I'll do my best on anything else that comes in. in the meantime, like this week, before I put out test 2. Okay. Well, all right. So I will stop recording at this point, and I will see you for lesson 28 on Wednesday.